Stanford University.
Welcome to EE380, Spring Quarter 2009-2010. I'm Andy Freeman. Dennis Allison and I organized this class. Bit of administrivia. We're approaching the end of the quarter. If you haven't kept up, it's going to, well, you've got enough time to catch up. Next week's speaker is Professor Hennessy on how technology in the university is changing. One of the classic technology stories involves standardized transistors. Back a long time ago when transistors were discrete elements, a company was trying to convince its customers that they really didn't need 1,000 different transistors, each one specialized to each application. The customers were pushing back saying, no, we do need these characteristics. It's absolutely crucial to what we're doing. Then the company said, but what if it cost 1/10 as much? The point being that low cost, like low power and low almost everything, has a virtue all its own. Display technology is no different. We've gone from segmented LED and LCD displays through CRTs to LCD panels and the like. There's even an iPhone app that looks like a digital clock with a Nixie tube display, for those of you into retro computing. However, one of the oldest display technologies is paper and paper analogs such as other sheets and films, which has wonderful properties. And it's very inexpensive to produce. However, the rewrite time is horrible. Today's speaker, Carl Taussig from HP, will speak to us on technology that is addressing that issue.
Thanks, Andy. So I'm the director of advanced display research for HP, and although HP doesn't manufacture displays, displays are hugely important to our business. We sell 65 million displays last year. I think that's probably more than anybody else in the world. We also have a big $24 billion printing business, to which the evolution of content or to digital formats proposes a big threat. And so from that perspective also, we're very interested in that. But of course, in addition to being a strategic threat to printing, the idea of printing displays is something that is technologically adjacent to a lot of things we know about. So almost all of our research on displays at HP is focused on, in some way, plastic. If it's not on plastic and can be put on a roll-to-roll process, basically it isn't happening. So with that as a kind of a preamble, although we're investigating a number of different types of display technologies, emissive, we do work on OLED, as well as these reflective displays we'll be talking about today. I'm going to really focus things on just this topic about the paper-like display and some technologies that we're developing to, as Andy mentioned, to really lower the cost. Because fundamentally, once you start moving from the $100 per square foot cost of a LC display down to the 1/10 of a cent per square foot per paper, somewhere in between there, paper becomes irrelevant because of the additional utility of a display. So that's kind of where we're heading. The work I'm going to be presenting today is actually a collaboration between HP Labs and FICOT, which is a spin-out that we formed with PowerFilm Solar. PowerFilm Solar is the world's only manufacturer of amorphous silicon solar cells on plastic with a roll-to-roll process. They're a spin-out of 3M some 20 years ago. And they've helped us a lot with the platform for depositing materials with vacuum deposition, which was a beginning point for the sale process I'll be talking about later. So I want to talk a little bit at the beginning just about what are the attributes about a paper-like display. And to do that, I think we got to kind of think about where, what is paper and what's a conventional display, and where do things fit in here. And these are kind of like what we see as the really desirable aspects about paper is that you really want to have it kind of be able to see it in we get kind of used to the fact that we can't really see our displays outside, but they'd be a lot better if we could. And we get used to the fact that the glass is really horrible stuff, that if you drop these laptops, they break, and that it's horrible to make things on it. In fact, we get the order of returns we get at HP for laptops is actually kind of surprising to me that glass breakage isn't the first one. It's actually number 3. The most frequent cause for returns is actually that there's nothing wrong with them. It's some kind of operator error, or it's Microsoft's problem. It's kind of interesting that we're in the HP room, but it's in the Gates building, and I think that's kind of a paradigm that at least we kind of live with. But anyway, different story. So yeah, plastic is going to make things a lot better. It's lightweight, it's mechanically robust, but I think also we're really going to get down to something in that cost thing. And it's always difficult if that's your sole proposition, is that you're going to lower the cost of an incumbent technology. You're probably beating your head on the wall or laying down in front of a train, because really, if you don't have something else to offer, you're never going to get that opportunity to disrupt, because an entrenched technology that can do everything you can is going to be difficult to push aside. So we also have some opportunities to do some things better than paper. Clearly, we're going to have an updatable medium of some sort, whether or not it's video, near video, or it's sort of Kindle-like, an ebook. It still has utility, much more than trying to rewrite a piece of paper, right? Color, that's kind of a transitional thing. People are certainly willing to do a lot of things. We live with black and white newspapers for years, but color has gotten in there. So this is kind of things we'd like to have, and some things we really have to have.
What constitutes a page-like display there? I mean, a Kindle's just another LCD.
A Kindle's not an LCD. A Kindle has an electrophoretic front plane. It's a very different display technology. It's reflective. It's not backlit. Today, the problem with a Kindle is that it's built on top of an active matrix backplane that's on a piece of glass. And it's married to glass, but it in itself is a piece of plastic. And in fact, we've built the world's first roll-to-roll displays, and we've used that same e-ink front plane for those. So e-ink, there's nothing wrong with in itself for plastic displays, but to date, there really isn't a good backplane technology that matches that. So what kind of things are going to drive this? And I think a lot of it is just that trend, the secular trend towards mobility. We want our information with us all the time, anywhere. We want to see it any place. And to have that mobility, then you also want to have all those other things like ruggedness and infinite battery life, and make it huge, make it small, all those things. The picture here shows an example of something called the Radius, which may or may never see the light of day. It's a spin-out of Philips Labs that's been trying to make this kind of the world's first rollout display. They were partnered with the Italian Telecom. And that's kind of an example of sort of what you might start thinking about if you could, this idea of a window shade display. Another factor that's really driving this, I think, is, and it's a very important one to me personally, is just the whole trend towards sustainability. And we'll talk more about that. And this isn't a message that actually the CTO of our printing business and I really see straight line on. So HP maybe speaks with several voices here. So this is coming from HP, the research part of HP, not the printing business. But we print way too much stuff, and there's really no need for it, and it has to stop. So enough said about that. So let's talk a little bit more about this whole paper thing, the paper crisis. It's a very energy-intensive industry, and a huge amount of what we're putting into landfills is paper, and a lot of that is printed paper. So all these things are kind of pushing us from the sustainability along with this mobility thing. Both these things are kind of crowding us into wanting to do that. And when these slides, I got some of these slides actually from Mike McCrary, the CTO of e-ink, a couple years ago, and it's really interesting. This was before the release of the Kindle. In fact, what they were showing at that time, the only product that had been released was this sort of stillborn Sony e-reader. And but the message was really still true, is that certainly as people in academic environment, you appreciate how wonderful it would be if we really didn't have so many textbooks, if there really were an option to get something that was really a good digital solution to that. newspapers are clearly the front and center target. Newspaper subscription rates have been declining over the last few years as even the kind of poor solutions that are available today have started to displace them. You're seeing it on your phone or your laptop or whatever, but subscription-based models for digital content with the appropriate appliance seem like an important opportunity. And I think the Kindle, now there's some 3 million of them out there. I think they're starting to demonstrate that. So from a user experience, it's a great solution. For the publishers, it's a nightmare because none of this whole migration to the digital display of media really takes into account how we're going to make up for these lost subscription values. So here's a little thought about where we go with all this, how this stuff goes from trees to garbage, and it really is kind of a poignant thing. I'd really like to do something about that, and I think we really have the opportunity to do that with paper displays. And here's the kind of the problem and the benefit potentially from the newspaper's perspective for should this happen would be that there's a lot of their costs really are all associated with lugging around paper and printing things on paper. That's all it's a big cost to them. But at the same time, people and advertisers are willing to spend a lot more money on conventional print than they are on digital print, and how to make up that gap and still have a role for publishing. Maybe conventional publishing just has to go away, and that's not the model that we're going to get our information from in the future. It's kind of an unanswered question at this point. So the next thing I want to talk a little bit about is, as we started talking about the ebook readers and the Kindle. So is everyone pretty much familiar? Has everyone at least looked at a Kindle? Can I show of hands? How many people have seen one, right? Sure, so everyone's kind of seen one. So some of the real...
I'd like to ask how many people have one. That would be also...
Yeah, well, who has one? So interesting. Not to be disparaging, but I noticed that it's usually in crowds that go like this that older people are actually the early adopters of the Kindle, which is interesting to me. I was able to get my mom hooked on it actually, and that was surprising to me because she's sort of a Luddite. And I think a lot of it is that it is a very easy device to read, and for those of us that are getting on in years, I think the reading experience is a lot better than LC, and that kind of helps. But one of the things that's really missing is to get color into that. I think you could get a lot deeper penetration if you could do color. But to do color with a reflective display is technically a very difficult problem. If you think a little bit first how it's done in LC or in projection, what we're doing is we're taking a white light typically, or in any transmissive mode I should say. Emissive is a different story. But it still has the same attributes in that we stick basically a color filter in front of a white light. So that means that if we want to have green, we're really only having 1/3 of the surface that's participating in that. But it's really not a problem because we got a backlight, so we just crank it up so enough light comes out of it that we still have a bright image. Now the problem is that if you do that with a reflective display, the only light you have to come back to you is the light that reflects on it. And then modulo, there's the optical losses in the medium itself. So then what you get reflected back to you is really going to be a lot less than even 1/3 of the light that's incident. And so if you just take e-ink and you put a color filter in front of it, what you end up with is a pretty terrible color. You kind of say, is that black and white or is it color? Because it's kind of hard to tell. So in order to get better utilization of the area that you have to serve as your reflector, we have at HP have been working on the idea of stacking. Of course, this isn't really anything that new. I guess the Fovio, a company a number of years ago, was trying the same approach with sensors, optical sensors. And there, if I want to make something blue, if I do this right, I have the whole surface participating in blue, so all that blue light can be reflected. But the problem is if I'm stacking these layers and there's losses in between them, if I do it in an additive way, I can't really get all the light back out, so my white point isn't that great. And if I use a subtractive approach, well, then I really can't, I really don't get a good solid black. So those are challenges. It's really a difficult systems problem. And if you think about it, by the time you've stacked these layers, it isn't really like 3 layers. There's all kinds of other stuff in there. Depending on the electro-optic medium that you're using, you may have, wave plates in there or other, reflectors or other layers. And so it wouldn't be unreasonable to think that you had something like, maybe 13 interfaces that light had to pass through. And you can index match them, but you're still going to have losses. If you have as small as, say, 2% loss, and then you do a round trip through that, we got 26 passes, so even 2% loss, you're down below 60% reflectivity. Now, 60% reflectivity is actually pretty good. Paper's not, typically a lot higher than that. It's got a nice Lambertian reflectance, but it's a difficult problem. And to address this, what the approach that we have taken is to manage the light carefully in the stack. And so what we're trying to do here is to have the light proceed through the stack only as far as it needs to. So, for example, if I want to have my blue light, I might have a yellow absorptive layer, and then which can either then pass blue light or absorb blue light. And then I don't want that blue light to go any further in the stack. So now I have sort of a dichroic mirror that's going to reflect the blue back from that interface, and it doesn't go through the rest of the stack, and so on with the different layers. And by doing that, I can gain back about 20% of the loss that I have if the light passes through the entire stack. So how good do we think that a reflective display really needs to be? Well, there's a number of, we kind of coming from a printing background, we tend to think about things with print standards. And there's two relevant print standards. One is what's called SNAP, which is the specification for newsprint advertising production. So that's kind of like what you see in USA Today, that kind of level of color, or the funny pages in the Sunday paper. And then there's SWAP, which is the specification for web offset printing. So that's more what you see in a high-end magazine. So that's really high color, like a high-quality color, like you'd expect from a photo printer. And I think that the idea of ever getting really to the quality of the SWAP standard is going to be very difficult, just because of the realities of what it takes to do reflective color. But the SNAP specification, which is shown there on the circle on this plot, let me take a little bit of time just to explain what this plot really is. Even in a color display, the first thing that we really perceive about it is actually the reflectivity. So on this axis, we're showing L star, which we can interpret as the white state. So 100% is a perfect white. And then the second thing that we really see in a display is contrast, black or white or color. So on this axis, we're plotting the difference between the white and black states, or delta L star max. And for reference then, that the SNAP standard I was talking about is shown there in circles, in the circle. That region above it is all kind of gravy. And here's kind of where some of our efforts are. And the star here is actually what happens if you put a color filter in front of e-ink. And that's going to give you, and actually almost anything else you'll see out there. There's a number of color reflective displays that have started to show up. Pixel Chi, the Flepia that's been introduced based on Kent's cholesteric LC material. And all these are going to be kind of way down this quadrant someplace. Fundamentally, any of these technologies that are basically space multiplexed color, color filter type arrangements are going to suffer from that same effect. So I'm going to show, and I'm not sure, I'm going to try showing this a couple ways. I'm going to just show you guys a little bit about what we've come up with this technology that we've been developing. I have a video, and I also have the real deal here, and I may ask to switch to that. You can come up after the talk or during the talk if you like. It's fine with me. And look at this. Hopefully this is going to work. Just thinking about it. Well, I hope the rest of mine, I tried one of them out before that. Maybe we'll switch to live. Let's switch to overhead. Can we do that? That doesn't come out so great. Yeah, it doesn't really do it justice, though. Yeah, I don't know. These lights come on over here?
Big true lights.
Yeah. Well, but now you can't see that. Well, so there you go.
You can see more
Oh,
color.
we can see it on the monitors.
Yeah.
Oh, okay.
Monitors are actually pretty good.
Yeah.
Now you can see that demonstrator.
Color, lots of color.
Yeah, so basically the purpose of this demonstrator is to show the black and white points of this are pretty much the same as e-ink. It's not using an electrophoretic medium. It's a different electro-optic effect that we're working with. But what we're adding to that is color that's reasonable. And the other thing that we're adding to it is actually near video rate. So those are two important things. That has to be done, we believe, without compromising the power consumption. Because if you give up on that, I mean, that was one of the big benefits of a reflective display is it's just not using any power when it's on. Most things like e-ink that are in that space, reflective displays today, are also bistable, which gives them a second mechanism for saving power, which is that in order to maintain a fixed image like a page that's being displayed doesn't require any any power. So that's the other vector by which you save power, and certainly technologies that we develop have to have that same set of things. Now I've completely hosed my laptop here, so I'll figure out how to get out of this one. Probably want to restart my presentation. See if this is still here. No. We're getting an extended demo here. All right. The curse of Microsoft on me. Well, I think we're just going to have to do the kick the plug here. So that's actually kind of at the end of what I was talking about in terms of reflective color, and I'm going to be moving on to talking about actually what we see as one of the real key enabling technologies that needs to be developed, which is how to manufacture electronics on flexible substrates. So that's really talking about making transistors with a roll-to-roll process, printing transistors. A lot of people are doing that in different ways. HP has developed a process based on imprint lithography. And boy, this seems like years. We actually started working on plastic displays or plastic manufacturing about 10 years ago. At that time, our interests were in making low-cost memory. At that point, we started to learning about that what it means to go against an entrenched competitor. Because at that time, flash was still really expensive. But the problem is that with plastic in that application really was only competing in one dimension, which was cost. We had to be able to basically beat silicon in cost, and that was a very difficult place to be in. And so about 4 or 5 years ago, we decided that displays were much a natural place to introduce plastic because they're instead of dealing with basically a fixed number of transistors you need for a function, you're dealing with a fixed area you need. And so if you can beat the areal cost, at some minimal resolution that's required, you're going to win. So I think since that time we've seen, that was back in around 2004, and at that time people were still pretty lukewarm about the idea, but I think since that time we've seen basically all the major display manufacturers now all have programs, if not about roll-to-roll manufacturing, certainly about plastic-based manufacturing. The standard approach in the industry is to take a piece of plastic and put it on top of a sheet of glass and then try as best you can to run it through your conventional process. And certainly that's been demonstrated as a feasible method for producing a plastic display, but it'll produce that display at a premium of the cost of building the display on a piece of glass. So it's not really clear that that really gets you to fundamentally the reason why you wanted to use plastic in the first place. So when we started the project, what we did is we said, let's just throw out everything. We didn't know anything about making things on glass, so it was pretty easy not to have that legacy to carry around with us. So we just kind of had a clean slate and said, let's just look at how you do it if you didn't know anything better. Now we did know about printing and about the different methods that you might use for that. So in some ways that was, I hope I'm not going to hit the wall here again. The reasons why you might want to go to it, basically, it's really about cost, and in many different aspects, and we'll be talking about all those. Certainly the fact that plastic is cheaper than glass, being that if nothing else, it's 40% for the same area of the weight. That's important because it's maybe 50 microns instead of half a millimeter, and it's much less dense. And to first order, that's going to produce everything else in your manufacturing process is going to scale with that. So at the end of the day, you have a pretty big fundamental advantage. But then the actual processes, and again, moving from a batch process to something that's steady state is huge. And then changing the paradigm of the clean room. So, and we'll talk about what we mean by that. And then, well, what about the equipment? Is the fact today a Gen 10 glass fab, that's something that makes displays on a 2x3 meter sheet of glass, costs about $2 billion, and we hope to do a lot better than that. As I said, we looked at a lot of different technologies for how we might do this. Photolithography was certainly the incumbent technology in the display area, but we looked at things we knew about like inkjet and maybe physical masking or laser direct write, and came up with this idea that imprint lithography in a roll-to-roll environment really made sense because it was really a lot like flexo or offset printing. So as a tease, I'll kind of, later on maybe we can kind of, just kind of get you guys an idea about what we're talking about here. Kind of goes on. This is a bunch of backplanes that we use for test, and we'll be talking a little bit more about how all this actually happens. And what we want to look at that. Okay. So this process, which we call SAIL, is really key because it actually solves the hardest thing about plastic is that it's dimensionally unstable. It's not flat to start with, and you do anything, you look at it cross-eyed, and it'll change its shape by hundreds of parts per million. And if you're trying to align micron scale features over meter distances, 100 parts per million, that's a non-starter. Okay, you're just not going to be able to do it. So people are doing all kinds of things, optical distortion, to try and make photolith work on this, and you have it nailed down to this piece of glass. It still moves. It's still very difficult. So we came with a completely different way of doing it. We can switch back to the slides. Where the process flow, we start out by taking a piece of plastic and putting in all the device deposition layers without any patterning. So the whole TFT stack, everything we need to make the whole backplane is deposited as a series of unpatterned films. Then we do an imprint process on top of that, and then we do a series of etches after that. So that's very different than the conventional process flow where we deposit one layer at a time, pattern it with photolith, and do another deposition, and so on. Let's see, I think I have... As I said before, we're partnered. FICOT is a spin-out company that's a derivative of PowerFilm. PowerFilm makes solar cells. So they already knew about how to put amorphous silicon on plastic with a roll-to-roll process. And they're doing that, as you can see here, these orange and purple cans are about the size of a boxcar. And that's what the devices on third meter or meter wide substrates that are being used to deposit those films. So that was a great place for us to start, and we initially put down our TFT stacks using that equipment. Once it's been deposited, we use this process called imprint lithography. So many of you might be familiar with a company called Molecular Imprints, which is kind of challenging the electronics industry to actually, for the highest possible resolution. You know, are we really going to, if you really need to make features that are tens of nanometers, maybe imprint becomes a way that's better than deep UV. That hasn't really panned out necessarily, but we think for roll-to-roll processing on plastic, it's ideal for a few reasons. So what we do in this process is we take the stack of films, we coat it with a UV curable photopolymer, then we emboss it, or it's actually more, it's a fairly low viscosity, 10 to 50 centipoise type fluid. So mostly it's a capillary filling action. We bring a rubber elastomeric stamp in contact with it. It takes on the shape of that stamp. While it's in contact, we fix it with UV. It separates. All this happens in a roll-to-roll environment. And then you're done. You have a pattern. And what you have there that's unique is that there's three things about this that are important. One is that it's very high resolution. Those lines up there, I think, are 40 nanometer lines that we imprinted on a piece of 50 micron thick plastic with a roll-to-roll process. So it's got very high resolution, much higher than we'd ever need. It has high throughput. Our machines run about 5 meters per minute, which for a printing press isn't that fast, but for a lithography tool, it's blazing. I have some video on that, which I don't know if I'll try and show you or not. The next thing about it is you don't have to just make a binary thing like a photomask. You can make a three-dimensional structure, so you can mold fancy things. And what's the advantage of that is that you can actually encode all the patterning information that you want to put on in multiple heights of this three-dimensional stamp that you put on. And that solves this key challenge in terms of the alignment issue that you have with stretchable plastic and allows us to have a self-aligning process. So on the upper row, what's shown is the problem you end up with a conventional type of process where you have distortion in your web between different patterning steps. And at the end of the day, you know, it's a misregistration problem in electronics or color separation in printing, and basically what happens is you get an unworkable device. If you can encode all your patterning information into a single monolithic structure that's molded once at the beginning of the process, then any process-induced distortion will distort essentially the mask as well as the substrate, so alignment is preserved. And that's really the key to how this works. So here's kind of an animation showing working through the steps of that. So what we have in blue and down are all the device layers that we've put down. And on top of this is a molded structure, this three-dimensional thing. And the way we transfer the pattern information is alternately by etching the mask and then the device layers. We go back and forth. We'll etch the mask some, we change the shape of what's being covered, and then we then in turn transfer that into the relevant layers of the device. And I'll just kind of go through this real kind of quickly showing how we're going back and forth, and you probably won't catch it all from that. But at the end of the day, what you end up with is here is shown a single pixel. In the upper left region there's a transistor. There's some gate lines in the magenta and data lines in blue, and a pixel. So there's a trick in here because how do you create a crossover, which is kind of the fundamental thing you need to do to be able to make something like a backplane. And we borrowed something from the MEMS world, given that we have a very high resolution process. We can mold features much finer than what we actually need for device. So by doing that, we can actually do basically what you do in the accelerometer world and undercut a structure, and that allows us to form crossovers. So there's a hidden benefit to actually taking out all those photolithography steps that are needed to make displays that we weren't really thinking about when we were thinking about solving the distortion problem. And that is that the repeated applications of photoresist in the display world are the biggest part of the cost. They're the biggest part of the cost from the materials perspective, from the equipment perspective, and from the time perspective. And so if you can get rid of, consolidate those into a single step, you're going to save a lot of money. So in addition, we feel like not only is the end use going to displace paper and be a green thing, but actually the manufacturing of the display compared to the way it's currently done is also a big step in the right direction. And again, it starts with this idea, the notion that the zeroth order rule anyway in sustainability is that take the mass out of it, and then you're going to do a lot better with everything else, because all the energy you have to put into it, All those things all scale with the mass that's involved. Also, another advantage to a lot of these things is that you're using low temperature processes, because that's what you're stuck with when you're working with plastic, and so you're going to save there. Another thing we're going to talk more about is equipment, and the nature of roll-to-roll processing is wonderful that way, because it's very compact, and the equipment handling issues are way straightforward compared to what it is for handling large sheets of very thin glass. So one of the things, though, and I didn't bring a core with me today. This is, I guess, about 3 inches it looks like. We usually use a 6-inch core to wrap plastic around. So we get it on a spool. We can put a kilometer of plastic, 50 micron plastic, on a core that's 6 inches, and the whole thing weighs about 40 kilos. It's about this big. And then you start thinking about that. That's like, 300 square meters of materials if it's a 13-inch wide web. And that's, if you think about the equivalent amount of glass and what it takes to store that, move it around, handle it without breaking it, starts to get your mind thinking about, why it's going to be a cheaper way of doing things. So another neat thing, though, about having the plastic stored that way, wrapped up tightly like a roll of toilet paper or whatever, is that it protects itself from particulate contamination. So when we're dealing with big pieces of glass, or with silicon wafers for that matter, we do it in a clean room because we're exposed. Every time we move this surface around, it's vulnerable to particulate contamination. Because the web rolls itself up, it's protecting itself from that. So our theory and what we're operating on is that we're going to only have locally clean environments inside our tools. We have a leader, which when we're threading the tools and they're open, may be exposed to contamination. But then we start a process, and in the case of a wet or an ambient process, we'll have HEPA filtered air. And so when that condition is supplied, then we do a process. Then we kind of wind the leader up, transport it through a dirty environment, which is a cheap environment, then put in another system, maybe a vacuum system. Of course, when we evacuate that, that's also clean inside, and we can run a process in there. So getting rid of this intermediate step with the clean room, having the clean room be pervasive around the tools, and getting rid of that can dramatically lower the cost of the factory. And we've been actually justifying this or validating this because we're actually building these displays right now in our facility while they're renovating the building for earthquakes. So we've had 2 fires, a couple floods, and a lot things I wouldn't even describe while we're actually doing this without a clean room. So that's been a challenge. This shows a kind of, again, getting at the idea of the sort of difference between handling, Gen 10 glass. Remember, this thing's a 0.5 millimeter thick. So it's an incredible, this industry is unbelievable if you really think about what it is that they're doing and how, even 10 years ago, if someone said you could do that, no one would have believed them. These tools are immense. So, and here's kind of an imprint tool. Sometime if any of you are interested, you could arrange with me to come and visit our facility. We bring a lot of people through there. And this is some of the substrate that we're showing here that's produced with that imprint. So another thing that we wanted to look at, first we kind of had the notion that maybe the scaling laws would be different for how, as you increase, so you kind of think about how, as you make a substrate larger, if you go from 150 to 200 millimeter to 300 millimeter on a wafer, everything's kind of growing like the square, and so the equipment costs are actually going up faster than that. And maybe the notion with the web is you're only making it linearly width, and so maybe the equipment costs are going to go down. Well, if the process speed is the same, it turns out it doesn't really work out that way. But what we did find when we've compared scaling, and what we're showing here on this plot is the cost. The blue cost is the cost of a panel stepper, flat panel stepper, versus the generation number, which can be also the size of the glass. And it also shows the reason why they're using bigger and bigger glass, because that's actually, driving down the cost, the actual cost of the equipment, because they can do more at once with fewer, changes in this batch mode. And these are the costs at equivalent capacity of the 2 imprint systems that we've put together. And what we find is that actually the scaling law is probably pretty much the same, but what happens is you're a couple orders of magnitude, in that case, down on cost. That's kind of a particular case because you're comparing what for us is a very inexpensive part of the process with what is the most expensive part of the photolithography-based process. So maybe a more realistic comparison comes from comparing the roll-to-roll deposition equipment, which our partner company is using for making solar cells, to the cost of a flat panel PECVD system. And again, you see kind of a similar thing, which is the scaling law looks actually remarkably similar, but again, the equipment costs in this case are maybe about a factor of 10 cheaper. Here's a kind of one of the things that when you want to get involved in this kind of a research problem, when you're doing roll-to-roll, the problem is there isn't really any way of faking it. You can't really do an experiment on a wafer in some piece of equipment you have. So your alternative is really that you have to actually build the equipment that you're going to use to develop the process. And so this is kind of a chronology of equipment that we've built. I'm going to cross my fingers and try and show something here maybe. This didn't work. Okay, so what you're seeing here is actually, this is the imprinting step that was used to generate these patterns on here. So it's kind of got this haze because we're looking through, this is a UV exposure, and we're looking through a filter, an eye protection filter that's on the side of the equipment. But it kind of gives you an idea what these processes are like.
Is that in the vacuum?
No, this is not. It's in a HEPA filtered environment. This system here, you can see, basically we open it up, we thread it all up, and once it's threaded, we close it up, start the HEPA filters. That condition cleans up the surface, and then we expose the clean part of the web through the process.
That's running at atmospheric pressure?
Yes, that one is.
Real time?
That was real time, yeah. Similar process here is, this is a wet etch process. Not a very good film, but I guess it's just showing it all kind of looks the same. And what does it look like? Well, what you're seeing is you just see little rollers going around and plastic moving through it. Okay, it looks like a printing press. All these things do. By contrast, I guess what I want to show is this is actually KUKA, there's a robotics company that makes a lot of this stuff. I think this may be Gen 10 glass. I'm not sure. But it's amazing when you think about what they're doing and how difficult this really is, to take that piece of glass and move it around. And if you look at this carefully, what you'll see is after it places, it almost looks like the video hangs, but really what they are is settling transients. And if you look at the reflection of that piece of glass, you'll see it just kind of starts shaking around. And again, on this, when they pick it up on this, I think you can see the edges of it kind of all flapping around. So the depth of field that they need to, if you remember from your kind of basic optics, that the depth of field is going like lambda over the numerical aperture squared. And so you got to hold these things. The finer the resolution you want to get, the flatter you have to have these things. And so they got to hold that sheet of glass flat within probably 2 to 3 microns over that whole 2 by 3 meter area. And so I think it's not hard to convince you about why that kind of a process is fundamentally expensive. But it is remarkable, nevertheless, and something that, as a mechanical engineer, at least initially, something I have a lot of respect for. So I guess all this is great. It's a good story, but if you can't actually make anything with it, then it's really not that exciting. And so I guess it was a year ago, this last February, that we demonstrated the world's first displays made completely with roll-to-roll processes. Again, this was done in partnership with E-Ink. We were using their electrophoretic medium. This is showing some of the amorphous silicon transistors that we use in these devices. And what we were kind of trying to prove with this graphic was actually one of the neat things is that we have this capability to make very high resolution structures. So we can make these amorphous silicon transistors all the way down to 1 micron channel lengths, which, if you know anything about amorphous silicon, isn't all that easy, a great a thing to do, because short channel effects kind of set in probably around 5 microns, and so you don't typically get your scaling benefit. And this is kind of, well, the mobility is also affected because the contact resistance tends to dominate as you get to shorter channels. That becomes a more important part of the equation. But anyway, these are basically a pretty good amorphous silicon transistor, as good as anything you're seeing in an LC display today. So in fact, we can make good devices. This is showing one of these demonstrators. This is like a 1,000 pixel demonstrator. Those are 1 millimeter pixels. That's E-Ink on the front. The reason I didn't bring it today is you could probably see it's actually part of a huge probe station. We don't actually currently, well, in another few weeks we will have our first bonded on a larger format displays coming out. But that's what we were showing 2 years ago. And this is kind of what it looks like when we're done. You can see there's actually a tandem 2 TFT design in series that are driving the pixel. And I guess what it is, one of the things is we're kind of, I guess, where the people were in the flat panel industry maybe 10 or 15 years ago, which is we're trying to bring up something that's pretty new and dealing with all that, the yields and working out the Paretos, and this is showing kind of typical kind of defects that we're dealing with. And so a lot of what we've done, and this is kind of a story about research in HP as a company, as we've moved away from being an internal manufacturer, there's much more of a burden on our internal research teams to carry things further so that they can be handed off to manufacturing partners. Some years ago, we would have been done with this project and off to something else, but now we're really having to move to pilot production inside HP Labs, which is kind of why we created the spin-out company. So it's been a fun problem for us because we didn't really know much about manufacturing, but we're learning a lot with MES systems, and a lot of what we're doing now is really all about how to identify defects, how to track them, how to understand, and how to clean up the process to get rid of them, which is really 80% of the battle. Coming from someone who's had a career mostly in research, I think I always had an appreciation of that, but it's really a lot more than I used to. So I want to talk in closing then just a little bit about where we're heading in the future, because amorphous silicon is great and you can make a lot of things with it. That's really what's in all the liquid crystal displays we have today. But in order to further reduce the cost and to further enhance the performance of certain things, you really need something with a little bit more zip than amorphous silicon. So mobilities for amorphous silicon are sort of like on the order of 1 centimeter squared per volt per second. But if you had about 10 times that, you could start doing neat things like integrating in your edge electronics, so your multiplexers and line drivers, into the actual backplane, and that can save a lot of the cost. And you can also start thinking about making more interesting kind of circuits for other applications, different kinds of sensors or detectors that maybe wouldn't be possible to do just with amorphous silicon. And of course, if you can get a complementary technology, then maybe you can, once you have a CMOS technology, then there's even more things you can do. So we've been studying what we're calling ZXO, or sort of zinc oxide based materials, typically ternary or quaternary material systems that have these characteristics. And actually one of the big advantages from our perspective is that they actually simplify our process. Because when we do a patterning process, unlike in a conventional photolithography process where you pattern a layer once and you're done with it, well, we have all the layers to start with, so we have to pattern individual layers multiple times. So the more layers we have, the more etch steps, and it kind of is a multiplicative effect. So if we can get rid of one layer out of our stack, then we can save ourselves at least 3 or 4 process steps, which really has a big impact on the cost. And in the case of these zinc oxide-based materials, we don't need, in order to get a good ohmic contact, we don't have to have a degeneratively doped N+ layer, and we can just directly put a metallic contact on them. And by getting rid of that layer, it really makes a big difference on the cost. So we have made those with this same sale process. We're not to the state that we are with amorphous silicon in either our deposition capability, but they really look very promising, and we really think that's going to be the next step for us. It's also, we're using the same technology to make OLEDs, and in the case of an OLED, you really need to source a lot more current. And again, that's kind of taxing on amorphous silicon, but it's probably a lot easier to do with the zinc oxide materials. So along with that, our first route to commercialization isn't actually through an HP product. It's actually going to be working with the military. We're making something that we've been calling a Dick Tracy watch. So this thing is designed for the infantry. We're doing it under funded research from the Army Research Lab, and the idea is that it has it's part plastic solar cell and part display with, again, e-ink as a front plane. And the idea is that then this is supplying map and other critical information to the infantry guy in a very robust package that can really take the kind of abuse these guys have, and yet doesn't burden them. The typical infantry guy is carrying around something like 70 pounds of batteries for all the different gizmos they have. So anything they can do to get rid of that stuff is a big deal. And so hopefully in roughly 18 months, we're on the hook to be developing, pilot production quantities of this to the Army for evaluation. So I think that's about it. Just acknowledge the folks we're working with here, and I guess open up for any kind of questions that people might have. Yes?
I have in the realm of possibility question for you. Given this technology with the self-aligned imprinting, and is it in non-display applications, I'm thinking, is it possible to mold the subsequent result into, say, a sphere and maintain the integrity of the electronics?
Well, a sphere is challenging because you're actually having, if you think about it, you can bend something into a cylindrical form, but to actually create it into a spherical structure requires a little bit more in terms of stretching. You actually have to stretch the surface to a large extent. But what I thought maybe you were asking before, which is something that we're very interested in, is that the same structure that can be used to pattern the structure can also mold in other elements, particularly like optical elements, lens arrays, or microfluidic channels. So you can have an integrated system that for those kind of applications where you're molding both an aligned fluidic or optic structure on top of integrated electronics, which is the direction we do think is very exciting about this, but probably not something that's straight and center for HP, seeing as we're no longer an instruments company.
But it's in the realm of possibility.
Absolutely.
Could you explain a little more about how the different layers of the mask allow you to be equivalent to different
Masks.
individual masks?
Yeah. Let's see if we can go back to a little bit and maybe. Okay. So to mold this structure, we're actually using 4 different heights. And I know you said you don't have laser pointer. And
Actually, I do.
do you? Oh, okay. Let me scab that from you. Oh, thank you. Okay. So we have one side we call the gutter, and that's actually basically no imprinted material or very minimal imprinted material. Maybe it's a few nanometers that we kind of de-scum off. Then we have the next height, which we're calling gate metal, and that masking structure is going to basically pattern those levels that ultimately we want to have at the gate structure. The third height in our structure is the transistor channel height, and the highest molded part of the structure is what we're going to use to form our data lines, or Fernando. So each of these is a discrete height, and they're all separated uniform, in our case, step heights of about 0.7 of a micron apart. So as I deposit this, as I with my rubber stamp process, I mold this thing on here. Well, the first thing I'm going to do is use it as an etch mask, just as imprinted, basically. And I'm going to cut through all my transistor layers all the way down to the substrate. So that was the first step of my process. The next thing I'm going to do now is I'm going to etch my mask. And this was something originally that we were really worried about. Could we control this process well enough? Because what I need to do is I need to etch just the next step in that mask. I want to remove it, but I don't want to remove the one above that. So it means my uniformity's got to be such that I still have enough margin to have it serve as a mask once I've removed that next 0.7 of a micron. Whoops, wrong direction. So, and what I've done now is I've removed the layer that would cover what's ultimately going to be my gate lines. So I removed all the polymer from that. So now all this area is exposed, but nothing else is exposed. So the next thing I do then is I etch all the way down to the gate metal. So now I have actually, if I took off all the layers right now, you'd see that this area that's exposed is down at the gate metal, and there's gate metal also everywhere else underneath that mask. And so here's kind of the trickiest part of this process. Now I actually do an undercutting process. I continue to etch this aluminum until, actually that was done in the first step. So actually everywhere, I should have said everywhere, but underneath these little grill works is the gate metal. Because that was undercut when I actually cut down in the first step to the gutter, and that cut through there. Now again, I'm going to go back and etch my polymer layers. And this time what I'm exposing is actually the transistor channel area, which would then have the top metal and the N+ contact region, which I have to remove. So I etch those off, and then actually I'm pretty much done. That's all you need to form a simple, this is all you need to actually drive e-ink. It's actually pretty much all you need to drive liquid crystal. So you have a hold capacitor, you have a transistor, and then you have a cross-point addressing scheme where you have a select line and a data line going the other way. And the reason why this doesn't, it's a self-aligning process is because the only alignment is actually when I make that original stamp that I'm going to use. That has to be perfectly aligned. All the features have to be aligned when I do that. But then after that, after I put that down onto the substrate, I don't care how the substrate distorts. And in fact, it was kind of an interesting thing. The first arrays we built, the biggest challenge we had is that the things actually shrunk by not a few hundred parts per million, but by 1.5% due to a step that we didn't even know about that was in the mask making process. We had something that cured and it shrank. And we went through and we built all these things, and until we actually wanted to hook them up to conventional flex circuits and found that they weren't even close, we didn't realize it. But the process itself doesn't care. It doesn't care over the area of a display. It doesn't care over tens or hundreds of meters that you could imprint. So that's really the key benefit. I don't know if that answered your question or not.
I still don't understand about the crossovers. How do you differentiate between a connection and a non-connection on a crossover?
Okay. I had a
You
white.
can draw a picture.
Oh yeah, great. Let's try that. Have some paper.
It's
here.
paper.
I'll see if I can. Yeah, I got a fat marker here. So let's see. What I want to get, let's say, is a crossover. So crossover.
You will have to move your head a little.
Oh.
Actually, if you pull the chair over and sit down, that would probably be
All right.
the most comfortable way to do it.
All right, let's try that.
All these classrooms, these rooms were actually designed, yeah.
Huh. Okay, so I want to build an overpass here, right? I want to have, this is kind of fundamentally what you need to make a transistor or a crossover. You need this capability to be able to have this line going underneath this line and then not being connected to it on either side. So in our multi-step imprint lithography process, the way we do that is we kind of first pattern this cross with all the layers, right? So now we have a cross, but we have a cross on the top and a cross on the bottom, and that's not very useful. So the additional trick we do is we put a little hole in the areas where I want to actually create this crossover. And then when I actually cut the bottom metal, we use a wet process, a wet chemical process to etch the metal. And we continue to etch beyond when it's 100 or 50 nanometers thick. But I actually continue to etch it until I cut it sideways or undercut it, removing the material that's underneath these thin regions. And then so what then the bottom metal ends up looking like is it comes out like this. Maybe it has a little stub sticking out the side. And there are places like underneath the data lines where it still exists, but it's not connected to anything. And then in the top metal, I can pattern that back so that it really just looks like a straight line. Because it's I can make anything that looks like a ziggurat. If I want to make something crossover, I have to use a trick. And that's the key trick that's involved in making these underpasses. It actually is a great trick because compared to any other method, even photolithography, you always have to have tolerance for misalignment, which leads to overlap capacitance and inhibits your transistor performance. We can have virtually none of that because we can use this undercut process to trim everything back to basically zero overlap, which is another benefit for high performance. Well, I tried. I mean, it probably take you're welcome to come up and visit, and we can show you more about how it actually works.
How does your process compare to what NanoSolar's doing and what Joe Jacobson was doing 15 years ago?
Well, Joe Jacobson actually, who's a founder of E-Ink, was never really, and Joe's a pretty creative guy. He wasn't principally doing electronic backplanes. Mostly what he did was start E-Ink, which is an electrophoretic display, which is a completely different animal. NanoSolar is a materials company, and I think they're trying to make wet printed solar cell technology. I'm not sure if they're using what the actual material system they're using is. It's not CAD Telluride. It's probably the other one. But anyway, it's
They're not doing active devices.
they're making diodes basically for solar cells. It's not a solar cell is actually a lot like a display in that it's pixelated to some degree, but the pixels tend to be on the order of centimeters, not microns. So it's pretty different. They don't have the same alignment challenges.
Yield. At your kind of production rates, yield goes in the trash, and who cares? You can make this stuff by the mile, but if it's a continuous yield issue, I mean, can you tune it to the point where suddenly it clicks and everything's perfect for a while?
You pretty much have to do that, right?
It's the only way to get it to work.
Yeah, it has to do that, and that's both the challenge and the benefit of roll-to-roll processing is that when you establish the steady state has to be something that works. Otherwise, you're going to produce miles of garbage, and so that is a challenge. I don't think of it as there are proof points because we are solar cells are being fabricated not only by power film but by unisolar. This roll-to-roll on stainless steel substrates, and NanoSolar is trying to bring up production, even in the Bay Area, and Alan Heger's new company in Boston area is also doing roll-to-roll. So people are doing it, at least in solar now, and
Pixels, a missing pixel is not so bad in solar.
right,
Missing pixel in a display shows up. You guys have a
absolutely.
fundamentally harder challenge.
It is a challenge. It is a difficult thing, and the amazing state that's been achieved. 10 years ago, every display that was shipped had 3 to 5 bad pixels in it. That doesn't happen anymore, and so and this is a little bit of the innovator's dilemma. The challenge for us is to be able to introduce in applications where the yield that inevitably you're going to have when you bring up a new process is going to be suitable to sell stuff. And so things like shelf-edge label in retail or placards or bus stop posters where maybe you could be tolerant of some of those are going to be initial targets. Coming in straight on with your laptop display, that's not probably likely, right? Yeah, I think
Weight is a big advantage you have.
huge. I mean, everyone knows they're going to have it. Everyone wants to have it. You will have a plastic display in your laptop. There's no doubt about it. At first, it's going to cost you a lot.
Next step is, of course, integration of keypad and all that stuff next. You're going to have to put that in. What goes a display if it's not a touchscreen, too? Have you even pushed in that direction?
Believe me, I'm pushed in just about every direction. My boss, or my boss squared, Mark Hurd, is a very demanding man. I'm not sure what you're asking there. The challenges about.
Just you're engineering for display generation.
Yes.
At some point, the display people are going to say, "What about the touchscreen? Is it a delay or?"
There's a number of, if you look at how touch is moving, right now it's an overlay. That has certain drawbacks in terms of optical performance, right? You're ultimately cutting into that. Also, to do multi-touch, it becomes more and more challenging to actually do all the things you want to do. So I think that what they're calling basically in-screen, or basically using the backplane to image what's going on, is probably the way that's all going to go. Fundamentally, all those things can happen in here because we're really not doing anything different. Our backplane is pretty much identical to what's on glass today. Unlike, a lot of other printing approaches are using organics or something else, but we're using the same materials, we have the same resolution, and so ultimately anything they can do, we should be able to do. The caveat is, we're not able to do the same kind of, we're not going after microprocessors. We're not going to do that scale of integration with what we're doing. We don't see it as, because if you want to do 32 masking layers, it's not really feasible to have a 32 height. Yeah, so we're at kind of 4 levels now. I think we can see going to 5, maybe 6, but beyond that, I don't think we're going to do it.
Technology breaks down.
Yeah. Well, at least for where I can see it from now.
How do you make the mask?
Great question. Great question. Yeah, with difficulty. So today I have a 6-inch research fab, silicon fab, and today if I want to make a display that's no bigger than 4-inch, I can do that in my facility up the street here on Page Mill Road. I also have a partner that has a Gen 2 fab, and Gen 2 starts to get interesting. So that's like 350 by 500 millimeters, something like that. So I can do up to a B-sized master with that. But the idea is, with the precision tools that are available in the industry, either the flat panel industry or the silicon industry today, I can actually make something, that's very nearly perfect in terms of a mask. And so in the case of silicon, I'm using, deep silicon etching, anisotropic silicon etching to create a structure. And again, it's a weird kind of a hybrid because this is actually a mechanical structure, so think about draft angles and sprues and risers and how everything flows around. But we can etch all that into silicon. And then through a series of steps, we can actually transfer that into this elastomeric UV transparent material, which we wrap around a quartz roller. And that becomes our tool. And we can regenerate those things as they wear out with other ones cast from the same master.
So we've had some research here at Stanford, and I know elsewhere, on organic semiconductors and effectively printing process deposition. Right. This is very much the same thing, except you're using amorphous silicon. Have you been experimenting in the organic semiconductor area as well?
Yeah, but my take on organics is a little, well, let me go a couple directions on that. I'm actually not a huge fan of organics. I think that the direction this is going, inorganic materials and vacuum deposition on plastic is something, fundamentally a lot of people who are doing organics say will ultimately be too expensive a process to do. And I don't see that as being the case. And I see the benefits of actually enhanced device performance and greater stability. The issues with susceptibility to oxygen and water of most of the organic materials, most of the high-performance organic materials, you can get a stable organic material, but the mobilities are like 1. And to get something that's stable, it usually means that it has to be protected. So I'm a little worried about that. Where I do see the role, where I see it as being very attractive, not necessarily organic, but a solution processable, maybe an inorganic, is a great alternative to a vacuum deposition. If we can do a roll coating process to put down a semiconductor layer, it's attractive from a cost perspective. But yeah, I'm just one voice, but my experience has been that I kind of like inorganics.
Thank you. Can you discuss a little bit? You mentioned that your masters wear out. What do the errors look like? Is it a thumb size error, or is it 4 pixels?
We got every kind of error you can. Yeah. So wait, masters. Okay, the terminology here. The master is the fundamental thing that we cut into either on a glass plate or on a silicon wafer, and those don't wear out. What wears out is the actual elastomer that we're using to produce the many impressions, cyclical impressions. As a target, we don't we've developed proprietary materials that can last for 1,000 impressions, which, well, it doesn't sound like very much, but that's a kilometer for us. So that's about a run length. So when we can do that, and what happens, it's a very interesting question actually. Typically what happens for us, the dominant failure mode with these materials is that there will be absorption of lighter weight or remnant solvents or other materials will leach out of the imprint polymer and will be absorbed by the stamp, and the stamp starts to swell. And after a while, it will distend into a shape where it actually locks into the substrate as it wears. And once it keys in, actually to a certain extent, and we've captured this with SEMs, it's pretty amazing. You can actually mold reentrance shapes, but you can only do that for so long, and you get these hyper extensions, and then eventually it'll actually pull pieces out of the stamp, and then you'll have a defect. And does it happen with a little place? Well, it happens all over the place pretty much all at once. So at the end of life, the thing just kind of,
Well, that's good. That's catastrophic failure.
Yeah.
You can't miss it.
Right. Well, if we go to the end of life of the actual elastomeric material, but in the interim, we can have all kinds of other defects in the printing. And probably the most dominant one there is particulate contamination. We call this the tent pole defect. So if for some reason a piece of dirt gets into the system and gets between this rubber stamp and the substrate, what it does is it forces the stamp away from the substrate and actually, like a tent pole, creates an awning that's much larger than the defect itself. So a 1 or 2 micron particle can create a defect that's 20 microns across. The fortunate thing about that is that these defects get cured into the photopolymer and then are convected away from the stamp. So the stamp gets cleaned up over time. Now, if the stamp actually got damaged by that interaction, then that will be something that will repeat in the printing process. And we can see those kind of defects. I mean, this is the kind of thing that Fernando, who's a part of our team, is working on right now. And actually, how do you develop vision systems to identify these things and track them? Can we do that online so we know when we're having the nice thing is actually is that a lot of the most of our defects are present after the imprint. The rest of the process kind of works them through. So if we image it, because all those patterns are all there right then, we can kind of see pretty much how it's going to play out. So,
So in terms of square footage, you said a kilometer. It's a kilometer by half a meter wide.
this is a 1/3 meter, and our tool set right now is all at a 1/3 meter. We don't, in research mode, as we're developing these materials, we're operating probably on lengths not that different than this, 2-3 meters at a time. We'll do for a run because this will represent what's different in some experiment we're doing. And there's billions of pixels in here, so there's no shortage of things to look at.
I'm just comparing that to a giant Intel fab in terms of acres per year. That's
Yeah, well,
roll
if you
out
come
something
up,
which is
if you come out to our facility, what you see is that I can tell you exactly how big it would be. Our pilot factory that we're trying to put together is 500,000 square feet per year, which is would make you about 1 million Kindles, okay? Which is about how many they sold the first year. We can fit that whole stuff comfortably into 2,000 square feet. So that gives you a little bit of an idea about how compact this kind of stuff can be. There's only 4 tools, and they're not very big. 4 different tools. It actually takes, because some tools are faster, like the imprint tool is very fast, you only need 1 of those. You need 4, vacuum deposit or etch tools to service that one.
But you only need one of each for the pilot.
Well, for pilot, actually, you still have the same problem. Let's say that the imprint tool runs 4 times as fast as a reactive ion etch tool. And typically, plasma tools are slower. The wet tools are slower. Kind of the slowest tools are the plasma tools. The wet tools are kind of in between. The imprint tool screams. It's very fast. So we take what was the most time-intensive part of the conventional process, and that becomes a non-issue. And now we're stuck with the other one. So you really need to have constant capacity. You need to have 4 of those vacuum tools for every imprint tool you have, or your imprint tools is underutilized if you want to have it in pilot. And I guess we're kind of pre-pilot now. We only have 2 of some tools. In the back?
So right now, the materials we fabricate is only for the backplane, right? And then you put the e-ink as the top. Have you thought about using other display devices other than e-ink?
Absolutely. We are also currently, another project that we have underway is we're making OLED displays with this too. And so what's exciting to us about that is right now, GE has stepped up and said, hey, we're going to be doing solid state lighting, OLEDs, and we have they've demonstrated a roll-to-roll process. And what we're thinking is great. We're developing a process so that we can take a roll-to-roll OLED substrate and a roll-to-roll backplane and integrate those without alignment and then have a display. And that's where we want to go with that vector. Now that's further out. Putting e-ink on this is unbelievably easy. You wouldn't believe it. I just take a piece of e-ink, it's like a pressure-sensitive adhesive, pull off a layer and stick it on, and I have a display. There's no patterning, no alignment. It's really, really easy to do that part. So it's a good place to start. But, again, I said the people paying for this research have high expectations for what we should be delivering. And so, yeah, we're really keen on OLED. We think that's a neat technology. No one display is going to be the panacea. There's not going to be a doomsday display. Sure. Well, a front light, you can put a front light on anything, right? You have a flashlight, then that does it, right? You could integrate something into a bezel. I don't see it as part of the putting a backlight and doing, say, a conventional transmissive like a liquid crystal type display. I think would not something that we're interested in doing. Fundamentally, one of the things that we like about either OLED or e-ink is that we have an opaque backplane. And we don't have to have an opaque backplane, but it's easy for us. We can use polyimide. That way we can use a high temperature process for our semiconductor deposition. This stuff will take 300 degrees C if we want. So we're not keen on having something transmissive, but anything reflective or emissive is kind of what we're looking at.
But then, of course, you can mix.
Sure. Yeah, absolutely.
So you have red coming up, and was it red on the bottom? I don't know what was on the bottom. You did.
Yeah. You can. You can actually, you certainly can make a not transflective, but emiflective, whatever that is. Yeah.
I don't know what it's called.
Yeah. There's a few ways of doing that. It's a pretty interesting idea, actually. Yeah.
So, what are your thoughts on? So, another way to make large area electronics is using inkjets.
Yeah.
People have been working on that, right? So, what are your thoughts on inkjet versus printing?
Sure. I'd love to talk about that. It's one of my favorite subjects to talk about. Again, as I kind of mentioned in the beginning, HP does a lot of inkjet, right? You'd think that, and obviously that was the first thing that we thought about doing. And fundamentally, I think almost any direct printing process, first, the great advantage is it's an additive process, right? I don't put on a bunch of stuff and then subtract off 90% of it. I like that. But even when you consider that, the real problem has to do with you're asking an awful lot out of those inks. You're asking for a material that both has to serve all the requirements of being jettable, either by piezo or thermal process, and then it has to perform as a semiconductor or something else, functional, a conductor. And that's really difficult to do. How do you make it do both those things? And as a result, these materials that are coming out now that are solution processable semiconductors are very expensive. So expensive that even if you put them down, they still cost more than a blanket deposition of amorphous silicon. Next problem, it's slow. It's a point-by-point process, so it's a direct write process. Third problem, the resolution's terrible. Even with a 2 picoliter kind of a drop, you're going to get like a 25 or 30 micron resolution. So I think inkjet has a role. I think for certain gross patterning things, it can be great, maybe color filter fabrication. But for actual, device fabrication, I don't think it's the best choice.
Do you think inkjet would be more expensive than roll-to-roll printing just because of the material cost?
The materials cost, the throughput, and just the capability. I just don't think you can actually do it. The alignment, you have to solve the alignment problem. And the smaller the drop size, the more you become suspect to things like stray charge that's on your substrate. The drop, this teeny drop now, it goes all over the place. It doesn't really go where you want. It's very hard to control. Yeah, I think it's actually even a feasibility question. I don't know many people in the industry that are really trying to do it with inkjet anymore. Most of them have gone to gravure.
Is it practical to do the lower layers of a conventional IC with this imprint process and then use the upper layers of the IC which have bigger features using
Yeah, I don't know. I'm not a wafer guy. Could be. It certainly is something that they're thinking about for glass, for a flat panel. People are interested in using it for combining some of the steps in a conventional LC process. It's possible, ultimately what we really want to do is just get it on plastic, right?
Yeah.
Yeah.
I think we're pretty much done. The tape went away, so.
Okay. Well, I'm happy to.
Stuff happens.
Yeah.
We have the room as long as you want to stay.
Anyone that wants to ask questions, I don't have any time pressure, so.
For more, please visit us at stanford.edu.